Welcome to DAR Tutors. We offer expert tuition in IB A-Level and IGCSE curricula. Today, we're going to explore some advanced concepts in inorganic chemistry, specifically designed for IB chemistry higher-level students. We will cover the naming of inorganic compounds, the properties of transition elements, the formation and properties of complex ions, including their color, and finally, how transition elements act as catalysts. By the end of this session, you will be able to apply stock notation to name complex compounds, explain the characteristic properties of D-block elements, detail how complex ions are formed and why they are colored, and describe the mechanisms of transition metal catalysis. Let's begin. Our first topic is the systematic naming of inorganic compounds. A key tool in this is oxidation state, which is used in what's known as stock notation. Stock notation indicates the oxidation state of a cation in Roman numerals placed in brackets immediately after the ion's name. This is crucial for metals that can exist in multiple stable oxidation states. A classic example is iron, a D-block element. Iron can have an oxidation state of +2 or +3. So we can have iron 2 chloride, where iron has an oxidation state of +2, and iron 3 chloride, where it has an oxidation state of +3. Notice that metals in groups 1 and 2, and aluminium in group 13, are exceptions. They typically have only one stable oxidation state, +1 for group 1, +2 for group 2, and +3 for aluminium. Therefore, their oxidation state is not usually indicated in their name. For instance, we simply say calcium chloride, not calcium R2 chloride, because calcium's oxidation state is always +2 in ionic compounds. Stock notation also extends to oxyanions, which are anions containing oxygen. For example, the manganate ion, MnO42, and the manganate ion, MnO4, contain manganese in different oxidation states. The oxyanion suffix -ate doesn't distinguish between them. So we use stock notation, manganate -- for MnO42 and manganate 7 for MnO4. This prevents ambiguity. Stock notation is also applied to name compounds between two nonmetals, particularly when they can form multiple compounds, such as nitrogen oxides. N2O can be named dinitrogen oxide using prefixes, but it can also be named nitrogen I oxide. Here the number of atoms is given, or the oxidation state. Similarly, SF6 is sulfur hexafluoride, or sulfur Vi fluoride. Let's work through an example to solidify this. What is the name of Pb3O4? First, we determine the oxidation states of lead. Oxygen's oxidation state is typically 2, so for 4 oxygen atoms, the total negative charge is 8. The compound is neutral, so the lead atoms must provide a total positive charge of +8. Dividing by 3 lead atoms gives a fractional oxidation state, which is not possible. This implies it's a mixed oxide. Research shows it's composed of 2 lead 2 ions, Pb2+, and 1 lead IV ion, Pb4+, combined with 4 oxide ions, O2. Therefore, the name is dilead 2 lead IV oxide. So, we've seen how to use stock notation to provide clear and unambiguous names for inorganic compounds by specifying the oxidation state of the central cation, especially for D-block metals and complex oxyanions. Now, let's turn our attention to the transition elements. Our objective is to define these elements and discuss their characteristic properties. First, what are transition elements? They are a subset of the D-block elements, located between group 2 and group 13 in the periodic table. A transition element is formally defined as a metal in the D-block that forms at least one stable cation with a partially filled D sublevel. This is the key condition. The first row of the D-block includes scandium to zinc. Let's see which of these are transition elements. Copper is a transition element. Its electron configuration is Ar3D104s1. When it forms a copper-2 ion, it loses the 4s electron and 1 3d electron, resulting in R3D9. This is a partially filled D sublevel, so copper is a transition element. Its copper-I ion, however, is Ar3D10, which is a full D sublevel. The copper-I ion is non-transitional. What about zinc? Zinc's configuration is Ar3D104s2. When it forms its stable ion, Zn2+, it loses the two 4s electrons, resulting in R310. This is a completely full D sublevel. Because the Zn2+ ion does not have a partially filled D sublevel, zinc is a D block element, but it is not a transition element. Scandium provides another interesting case. Its configuration is R3d14s2. The most common ion is Sc3+, which loses all three valence electrons to become R3d-Rho. This has no D electrons, so it is non-transitional. However, scandium can also form a stable Sc2+ ion with the configuration R3d1. Since it forms a stable cation with a partially filled D sublevel, scandium is classified as a transition element. This demonstrates that the definition hinges on at least one stable cation, not necessarily the most common one. Now let's explore the characteristic properties that arise from this partially filled D sublevel. Firstly, transition elements have high densities, melting points, and boiling points, significantly higher than S-block elements. This is due to the involvement of the 4s and 3d electrons in strong metallic bonding. Secondly, they can exhibit a variety of stable oxidation states. This is a direct consequence of the small energy difference between the 4s and 3d orbitals, allowing them to lose different numbers of electrons. Thirdly, they have a strong tendency to form complex ions, which we will discuss in detail shortly. Fourthly, transition metal complexes are often colored. Fifthly, they can act as catalysts. And finally, many transition elements and their compounds exhibit magnetism. To summarize, we have defined transition elements based on their electron configuration in their ions and identified their 6 key properties: high physical constants, variable oxidation states, complex ion formation, color, catalytic activity, and magnetism. Let's now address the property of magnetism in transition elements. Our objective is to distinguish between diamagnetic and paramagnetic substances based on their electron configurations. Substances can be classified into 2 main types based on their interaction with a magnetic field. First, we have diamagnetic substances. These have all of their electron spins paired. This results in a net magnetic spin of 0. Consequently, diamagnetic compounds are weakly repelled by a magnetic field. Conversely, paramagnetic substances have one or more unpaired electrons. These unpaired electrons create a net magnetic spin. Because of this, paramagnetic compounds are attracted into a magnetic field. The presence of unpaired electrons is determined by the electron configuration, specifically how the d orbitals are filled according to Hund's rule and the Pauli exclusion principle. Let's consider an example. Are zinc ions, Zn2+, diamagnetic or paramagnetic? We know the electron configuration of Zn2+ is R3d10. The 3d sublevel consists of 5 d orbitals. A full 3d10 configuration means each of these 5 orbitals contains a pair of electrons. Since all 3d electrons are paired, there are no unpaired electrons. Because there are no unpaired electrons in the 3d sublevel, the Zn2+ ion is diamagnetic. It would be weakly repelled by a magnetic field. Now let's compare this to an iron F3 ion. Is Fe3+ diamagnetic or paramagnetic? The configuration of Fe3+ is R3d5. When we fill the 5 3d orbitals according to Hund's rule, we place 1 electron in each orbital before pairing any. This results in 5 unpaired electrons. Since the Fe3+ ion has 5 unpaired electrons, it is strongly paramagnetic. It would be significantly attracted by a magnetic field. To recap, diamagnetism arises from completely paired electrons and causes weak repulsion, while paramagnetism arises from unpaired electrons and causes attraction to a magnetic field. We have seen how to determine this from the electron configuration of the transition metal ion. We've established that transition elements exhibit variable oxidation states. Our goal now is to understand why this occurs and the factors influencing the stability of these states. Transition metals can exist in many stable oxidation states because the energy difference between the 3d and 4s sublevels is very small. This means that not only can the two 4s electrons be easily lost, but 1 or more 3d electrons can also be removed without a large energy penalty. The maximum oxidation state is often observed when all 4s and unpaired 3d electrons are removed. For example, chromium, R3d54s1, has a highest oxidation state of +6. This corresponds to the loss of the single 4s electron and all 5 3d electrons. Manganese, R3d54s2, has a highest oxidation state of +7, corresponding to the loss of both 4s electrons and all 5 3d electrons. These high oxidation states are typically found in compounds with highly electronegative elements like oxygen or fluorine. The stability of a particular oxidation state is not solely determined by ionization energies. When a metal ion forms a compound, it either becomes part of a solid ionic lattice or becomes hydrated in solution. This process releases a significant amount of energy. The stability of an oxidation state is a balance between the endothermic ionization energy required to form the ion and the exothermic energy released when the ion interacts with its surroundings, either as lattice energy in a solid or hydration energy in solution. A higher charge on the ion requires more energy to remove electrons, but is offset by a much larger release of energy during lattice formation or hydration. This is why ions like Fe3+ can be stable even though it takes a lot of energy to remove that third electron. We can see the effect of this in an experiment. A yellow solution of ammonium vanadate, B, which contains VO3 with vanadium in a +5 oxidation state, can be stepwise reduced by zinc metal. Adding zinc and sulfuric acid reduces the V5+, which forms a yellow solution, to V4+, which is blue. Further reduction leads to green V3+, and finally to lavender V2+. Each color corresponds to a different oxidation state, providing a striking visual demonstration of the variable oxidation states of transition elements. We have now explained that the variable oxidation states of transition elements arise from the small energy difference between 3d and 4s orbitals, and that the stability of these states is determined by the interplay of ionization and lattice or hydration energies. We've frequently mentioned complex ions, so let's delve into their structure and formation. Our objective is to define a complex ion, its components, and the types of ligands that can form it. A complex ion consists of a central metal cation, which is typically a transition metal, bonded to one or more molecules or anions called ligands. The bond between the metal and the ligand is a special type of covalent bond called a coordination bond or dative covalent bond. In this bond, both of the shared electrons come from the ligand. Because ligands donate electrons, they are classified as Lewis bases. So, a complex ion is a central metal cation, which acts as a Lewis acid by accepting electron pairs, bonded to ligands, which act as Lewis bases by donating electron pairs. Common examples of ligands include water, H2O, ammonia, NH3, chloride ions, ClO, hydroxide ions, OHE, and cyanide ions, CN. These are monodentate ligands, meaning they form only one coordination bond with the metal. The coordination number is the number of ligands or ligand atoms directly bonded to the central metal ion. Common coordination numbers are 2, 4, and 6, and these correspond to specific shapes. Coordination number 2 gives a linear shape. Coordination number 4 can be tetrahedral or square planar, with tetrahedral being more common. Coordination number 6 almost always results in an octahedral shape. The net charge on the complex ion is the sum of the charge on the central metal cation and the total charge on all the ligands. This allows for complexes to have positive, negative, or even zero charges overall. For example, let's consider the complex ion formed when ammonia ligands coordinate to a copper-2 ion. The copper-2 ion has a +2 charge. Ammonia is a neutral ligand. If 6 ammonia molecules coordinate to the copper-2 ion, the overall charge on the complex is +2 + 6 times 0, which equals +2. The complex ion, CuNH362+, is called hexamine copper-2. The coordination number is 6, giving it an octahedral shape. We have now defined a complex ion as a central metal cation bonded to ligands via coordination bonds. We've seen how coordination number dictates the shape of the complex and how to calculate its net charge from the charges of its components. Beyond simple monodentate ligands, there are more complex types. Our objective here is to introduce polydentate ligands, also known as chelating agents. While monodentate ligands bind to a metal ion at only one point, polydentate ligands, or chelating agents, can form 2 or more coordination bonds with the same central metal cation. These ligands form coordination rings with the metal ion, and this process of ring formation is called chelation. Chelate complexes are typically much more stable than those formed with monodentate ligands, a phenomenon known as the chelate effect. Let's look at some examples. Bidentate ligands bind through two atoms. First, the ethanedioate ion, C2O42, often called oxalate. It can coordinate to a metal ion through two negatively charged oxygen atoms, forming a five-membered ring. Each oxygen donates a lone pair to the metal. Another bidentate example is 1022-diaminoethane, H2NEDCH2, CH2, NH2. This molecule, often abbreviated EPA, coordinates through the lone pairs on its two nitrogen atoms, again forming a five-membered ring. A very important example of a polydentate ligand is EDTA, ethylene diaminate triacetic acid. The EDTA anion is a hexadentate ligand. This means it can form up to 6 coordination bonds with a single metal ion. It coordinates through the lone pairs on its two nitrogen atoms and the negative charges on its 4 carboxylate oxygen atoms. EDTA forms incredibly stable chelate complexes. For example, when EDTA binds to a copper-2 ion, it wraps around the metal, forming 6 bonds. This hexadentate chelate, QEDTA2, is far more stable than a complex with monodentate ligands like water. To recap, we have seen that polydentate ligands, or chelating agents, can form multiple coordination bonds, leading to the formation of stable chelate complexes. This ring-forming behavior, or chelation, is a key concept in coordination chemistry. A fascinating property of complex ions is their color. Our objective in this scene is to explain the DD transition model, which accounts for the color of transition metal complexes. The color we see is not inherent. It's the result of how a substance absorbs and transmits light. When white light, which contains all colors of the visible spectrum, shines on a colored solution, the solution absorbs some wavelengths of light. The color we perceive is the combination of the remaining transmitted or reflected wavelengths. This is often explained using a complementary color wheel. On a color wheel, complementary colors are opposite each other. If a substance absorbs light of one color, its complementary color is the one we see. For example, if a solution absorbs red light, it will appear green. Now, why do transition metal complexes absorb specific wavelengths of light? It's due to the splitting of the 3d orbitals. In an isolated gaseous d-block metal atom, the 5 3d orbitals are degenerate, meaning they have the same energy. However, when ligands approach the metal cation to form a complex, the ligand's lone pair electrons repel the metal's 3d electrons. This repulsion depends on the shape of the 3d orbital and its orientation relative to the approaching ligands. In an octahedral complex, the ligands approach along the x, y, and z axes. The d orbitals that point along these axes experience stronger repulsion and are raised in energy. These are the dz2 and dx2y2 orbitals. The d orbitals that lie between the axes, dxy, dxz, and dyz, experience weaker repulsion and are lowered in energy. This interaction causes the 5 3d orbitals to split into 2 energy levels, a lower set of 3 orbitals, T2g, and a higher set of 2 orbitals, E or G. The energy gap between these two sets is called the crystal field splitting energy, denoted as dE. Now let's consider the titanium-3 ion in the hexaquatatanium-3 complex, TH2O63+. Ti3+ has a 3d1 electron configuration. In the complex, this single electron occupies one of the lower energy 2g orbitals. When white light is shown on the solution, the electron can absorb a photon with energy equal to dE. This promotes the electron to one of the higher energy Eg orbitals. This process is called a DD transition. The energy of the photon absorbed is directly related to its frequency and wavelength by the equation E equals chef. Hc, the TH2O63+ ion absorbs yellow light. Its complementary color, which is blue-violet, is transmitted. This gives the solution a characteristic purple color. In summary, the color of transition metal complexes is due to the splitting of the d orbitals into 2 energy levels by the ligands. When an electron absorbs light of a specific wavelength equal to the energy gap dE and makes a DD transition, we perceive the complementary color. The energy splitting of the d orbitals, and thus the color of the complex, is influenced by several factors. Our objective is to identify these factors and provide examples. There are three main factors that affect the energy difference, dE, and therefore the color. First is the ionic charge on the transition metal. As the charge on the central cation increases, it pulls the ligand electrons closer, causing greater repulsion and a larger dE. This typically leads to absorption of higher energy light, shorter wavelength, and different perceived colors. Second is the number of d electrons. D transitions can only occur if the d sublevel is incompletely filled. If it's completely empty, like in Sc3+, D or completely full, like in Cu+, D10 or Zn2+, D10, no dd transitions are possible. Such ions appear colorless because they don't absorb light in the visible spectrum. This brings us to the third and most significant factor, the nature of the ligand. Ligands have different sizes, charges, and electron-donating abilities. Strong field ligands, like ammonia, cause a large energy splitting and a large dE. Weak field ligands, like water or chloride, cause a smaller energy splitting and a smaller dE. This is often described by the spectrochemical series. A larger dE means the complex absorbs higher energy light, shorter wavelength, and vice versa. This is why ligand replacement often results in a dramatic color change. Let's apply this to a common reaction, the addition of ammonia to a copper-2 salt solution. The initial solution contains the hexa-aqua-copper-2 ion, QH2O62+, which is light blue. When ammonia is added, a ligand replacement reaction occurs. 4 of the water ligands are replaced by ammonia to form the tetraamine-diaqua-copper-2 ion, QH2O NH342+, which is a deep royal blue. Why does the color change? Water is a relatively weak ligand, so it causes a small energy splitting. Ammonia is a stronger ligand, causing a larger energy splitting. This means the complex with ammonia, H2O2 NH342+, absorbs higher energy light, shorter wavelength, than the complex with water, QH2O602+. This shift in the absorbed wavelength is what we perceive as a change in color from light blue to dark blue. So, we've now explained that color in transition metal complexes depends on the ionic charge, the number of d electrons, and the nature of the ligand, which dictates the energy-splitting dE and thus the wavelength of light absorbed. Understanding color and absorption leads us to a powerful analytical technique called colorimetry. Our objective is to understand how colorimetry can be used to determine the concentration of a colored solution. Colorimetry is a method that uses the absorption of light by a solution to measure the concentration of a colored substance. The process uses an instrument called a colorimeter or spectrophotometer. Light from a source passes through a wavelength selector, which isolates a specific color of light. This monochromatic light then passes through the colored sample held in a cuvette. The intensity of the light after passing through the sample is measured by a detector. This value is compared to the intensity of the light that went through a blank solution, which is just the solvent. The difference is recorded as absorbance. The relationship between absorbance and concentration is given by Beer-Lambert law, which states that absorbance, A, is directly proportional to the concentration, C, and the path length. B, the light travels through the solution. The key takeaway is this. For a given substance and wavelength, the absorbance is directly proportional to the concentration, provided the solution is dilute. To use this, we first need a calibration curve. This is the process of generating a graph of absorbance versus concentration. We prepare a series of solutions of known concentrations, often called standards. We then measure the absorbance of each standard at a specific, carefully chosen wavelength. This wavelength is typically the wavelength of light most strongly absorbed by the substance. It's lambda max, Lmax. For aqueous bromine, which is orange, we would use a filter that transmits blue light, its complementary color. Plotting these points gives a straight line. This calibration curve is our tool. If we then have a solution of an unknown concentration, we measure its absorbance. We find that absorbance on the y-axis, trace across to the line, and then down to the x-axis to read the concentration. This technique has wide applications, from environmental monitoring to clinical chemistry. We can also measure absorbance over time to track the progress of a chemical reaction if one of the reactants or products is colored. In summary, we have learned that colorimetry, based on the Beer-Lambert law, is a precise method for determining the concentration of colored solutions by measuring their light absorbance and comparing it to a calibration curve. Our final topic is one of the most important applications of transition elements in industry. Our objective is to explain how transition metals and their compounds can act as catalysts. A catalyst is a substance that increases the rate of a chemical reaction without being consumed in the process. It does this by providing an alternative reaction pathway with a lower activation energy. Transition metals are excellent catalysts, particularly in heterogeneous catalysis, where the catalyst is in a different physical state from the reactants. Think of the catalytic converter in your car. A prime industrial example is the Haber process for ammonia synthesis, which uses an iron catalyst. In this process, nitrogen and hydrogen gas adsorb onto the surface of the solid iron. Adsorption is the first step. The reactant molecules N2 and H2 land on the surface of the catalyst. Because transition metals have vacant d orbitals or unpaired d electrons, they can form temporary bonds with these molecules. This process weakens the bonds within the reactant molecules. Being adsorbed on the surface and having weakened bonds makes the reactant molecules more reactive. They are also held closer together, increasing the frequency of successful collisions. They react on the surface to form product molecules, which then desorb, or leave the surface, to continue the reaction. Essentially, the catalyst provides a meeting point and activation for the reactants, allowing them to react at a much faster rate. Another crucial example is the Ziegler-Natta catalyst, a transition metal complex of titanium and aluminum alkyls, used in the polymerization of ethene. It allows for stereoregular polymer synthesis at much lower temperatures and pressures. Transition metals also act as homogeneous catalysts, where the catalyst and reactants are in the same phase, typically solution. For example, iron 3 ions catalyze the reaction between peroxidous sulfate and iodide ions. The iron 3 catalyst is reduced to iron 2, which then reacts with the peroxidous sulfate. The resulting iron 2 is oxidized back to iron 3 by the peroxidous sulfate. The catalyst is regenerated. A dramatic demonstration of homogeneous catalysis is adding cobalt-2 ions to a solution of hydrogen peroxide and tartrate. The solution changes from pink to green as cobalt-2 is oxidized to cobalt-3 and back. This temporary color change indicates the formation of an intermediate complex that facilitates the reaction. To conclude, transition metals act as catalysts, primarily by their ability to use their vacant or partially filled d orbitals to form temporary bonds, weaken reactant bonds, and provide alternative reaction pathways with lower activation energies. It's been a comprehensive session covering naming, properties, complex ions, color, and catalysis. Before we move to practice questions, I want to briefly mention that if you need more personalized support in any of these areas, DAR Tutors can provide expert tuition in IB Chemistry HL. For expert tuition in IB A-Level and IGCSE curricula, please contact DAR Tutors. We can help you achieve your academic goals. Now let's test your understanding with 5 IB-style practice questions. Each will be followed by a fully worked solution. Let's begin with question 1. Question 1 asks for the name of the complex ion, NiNH34H2022+. We'll break this down using IUPAC rules. First, identify the ligands and their charges. Ammonia, NH3, is neutral. Water, H2O, is also neutral. Next, determine the oxidation state of the central metal. The overall charge of the complex is +2. Since the ligands are neutral, the charge on the nickel ion must be +2. Now, we write the name of the ligands in alphabetical order before the metal name. We have 2 aqua ligands and 4 amine ligands. A comes before Q. We use prefixes to indicate the number DEET for 2, tetra for 4. So the ligand part of the name is tetraaminidiaqua. Finally, we name the metal and its oxidation state in Roman numerals. Since nickel has a +2 oxidation state, we have nickel 2. The complete name is tetraaminidiaquanickel 2. The complex has a coordination number of 6 as there are 4 amine and 2 aqua ligands. Question 2 asks for the orbital diagram of the cobalt-3 ion, CO3+, and then to explain why it is paramagnetic. This combines electron configuration and magnetic properties. First, we find the atomic number of cobalt, which is 27. The neutral atom's configuration is Sasawamkis R374s2. To form the CO3 plus ion, it loses the two 4s electrons and one 3d electron, giving it a configuration of R3d6. Now we draw the orbital diagram for the 3ds configuration. We have 5 boxes to represent the d orbitals. We fill them according to Hund's rule, placing one electron in each orbital first, then pairing the electrons. This gives 4 unpaired electrons. So for part A, the diagram shows the 5 3d orbitals with 4 unpaired electrons. For part B, the explanation for its paramagnetism is directly related to this. A substance is paramagnetic if it has unpaired electrons. Since the orbital diagram clearly shows 4 unpaired electrons in the 3d sublevel of the CO3 plus ion, it will be attracted into a magnetic field and is therefore paramagnetic. This is the definition of paramagnetism. Question 3 asks us to explain why the aqueous copper-2 ion, CuH2O62+, is light blue, while the solid copper-2 sulfate, CuSO4, is white. This tests our understanding of the color and DD transition concepts. Let's first analyze the aqueous solution. The light blue color of CuH2O62+ arises because it absorbs specific wavelengths of visible light, its complementary colors, and transmits the blue light that we see. This absorption of light is possible because copper-2, with its 3-9 electron configuration, has an incompletely filled d sublevel. The ligands, water molecules, split the 3d orbitals into lower and higher energy sets. The energy gap between these orbitals allows for dd electron transitions. The specific wavelength of light corresponding to this energy gap is absorbed, resulting in the complex appearing blue. Now let's consider solid CuSO4. The question asks about the solid, not a solution of it. In solid copper-2 sulfate, the copper ions are not bonded to water ligands. There are no coordinated ligands to split the d orbitals. Without any ligands to split the d orbitals, there is no energy gap for dd transitions to occur in the visible range. Therefore, the solid CuSO4 does not absorb any visible light. When a substance reflects all wavelengths of white light, it appears white. So the key difference is the presence of ligands in solution, which cause the d orbital splitting necessary for light absorption and the generation of color. In the solid state without ligands, this splitting doesn't happen, and the compound appears white. Question 4 asks for the net charge of the complex ion hexahydroxyplumb-2. This question combines naming conventions with oxidation state calculations. First, we need to extract the information from the name. Plumbate tells us the central metal is lead. The Roman numeral 2 tells us the oxidation state of the lead, Pb, is +2. Next, hexahydroxo tells us there are 6 hydroxoligands. A hydroxoligand is an hydroxide ion, OHE, so each ligand has a charge of 1. To find the net charge of the entire complex, we sum the charge of the central metal ion and the total charge of all the ligands. The charge on the lead ion is +2. We have 6 hydroxide ligands, each with a charge of Ya1. So the total ligand charge is 6 times 1, which is 6. Adding these together, +2 + 6 = 4. Therefore, the net charge of the complex ion is 4. Our final question, question 5, asks us to explain what a polydentate ligand is and why it forms a more stable complex than a monodentate ligand. This tests your understanding of the chelate effect. First, for part A, a polydentate ligand is a ligand that can form 2 or more coordination bonds with a single central metal cation. Common examples include ethanedioate, 1,2-diaminoethane, and EDTA. Now for part B, the stability. Let's compare a complex with a bidentate ligand with a similar complex made with monodentate ligands, water. The reaction is a ligand replacement, where N replaces 2 waters. Consider the following equilibrium. QH2O6 plus En forms QH2O4NN2 plus 2 water molecules. In this reaction, a bidentate ligand replaces 2 monodentate ligands. The reason for the increased stability is primarily entropic. On the left side of the equation, we have 2 particles. On the right side, we have 3 particles. The number of independent particles in the system has increased. An increase in the number of particles leads to an increase in the entropy or disorder of the system. An increase in entropy is thermodynamically favorable. Because the change in entropy, DDS, is positive, the value of the Gibbs free energy change, Ig, becomes more negative, making the reaction spontaneous and the chelate complex more stable. That brings us to the end of this session on advanced inorganic chemistry concepts for IB Chemistry HL. We have covered a lot of ground today. We started with the systematic naming of compounds using stock notation. We then defined transition elements, discussed their key properties, and distinguished between diamagnetic and paramagnetic materials. We explored the formation and structure of complex ions, including polydentate ligands and the chelate effect. We saw how the DD transition model explains the vibrant colors of these complexes and how colorimetry is used to analyze them. Finally, we looked at how transition elements act as catalysts in both heterogeneous and homogeneous processes. I hope this has provided a clear and comprehensive overview. Remember to revisit the IB syllabus objectives and practice problems to solidify your understanding. Thank you for joining.